Well, we're building and building, and we're going to focus on some real-world type application problems, and all of these problems have come from a previous AP exam. So I'm really trying to give you hints on how to decipher what the problem is asking for. So pay close attention today. Alright, so I've got 6 examples here that we're going to put in our notebook and label each one appropriately. So our first example is increasing at a constant rate. Alright, so I want to draw a function that's increasing, it's on its way up, and the rate is constant. Now remember, rate is our 4-letter word for slope, which of course is equivalent to derivative. Alright, we're starting to find a lot of words that mean the same thing. Okay, so I'm increasing at a constant rate. So I would say a line is a great example of that. Clearly this line is increasing, and its rate or slope or derivative there is all constant. Basically, if you had to assign a slope to that, maybe it has a slope of 2. Okay, it has a constant rate. Therefore, f prime is greater than 0. Okay, and I know that because the function is increasing. Okay, and f double prime, remember, f double prime describes concavity. Does a line have any concavity? Of course not. So f double prime is equal to 0. Likewise, if a function's decreasing at a constant rate, okay, there's that 4-letter rate word, so the slopes are all constant, and I'm decreasing. Okay, again, I would have to look linear, which means f prime is less than 0. So I'm saying that the slope is less than 0. Again, if you had to assign a slope, maybe this one has a -2 slope. And a linear function, of course, has no concavity. It's not concave up or down, so the second derivative would be equal to 0. All right, so now let's look at things that aren't linear. Our next function needs to be increasing at an increasing rate. So you'll see this on our quiz all the time, and you'll have to draw something like that. So I need to be increasing, but my increasing rate, there's my 4-letter word, tells me that the slopes, remember rate is a slope, the slopes have to be getting bigger. So I'm saying that's going to look something like this. And now how do I know for sure? Well, if you had to put little tangent lines on that represent your slope, are those slopes getting steeper or less steep? The steeper I get, the increasing slope I have, the increasing rate I have. So I would say f prime is positive. Again, f prime refers to the slopes are positive, and the concavity is positive. Notice this looks like, if I had to take a piece of it, concave up like a cup, it's smiling. Decreasing at an increasing rate. Okay, now clearly your function's going down, but the rate, the slopes have to be getting bigger. Okay, the slopes have to be increasing. Now, sometimes the decreasing ones are harder for students to see. So basically, if your function's decreasing, would you agree it could look 2 different ways? Basically, I could be decreasing and concave up, or I could be decreasing and concave down. Now, one of those has slopes at an increasing rate. Picture drawing tangent lines on there. Whose slopes are getting bigger? You want your slopes to increase. Okay, now remember, this is a very negative slope and it's getting closer to 0. Picture a number line. If you're very negative and you get closer to 0, you're getting bigger. This one is 0 and they're getting more negative, that's getting smaller. So I'm going to scratch this one and say this is what my picture would look like. It's clearly decreasing and the slopes are getting bigger. So that tells me my first derivative is less than 0 because I'm talking about slope. And my second derivative is greater than 0 because I'm talking about concavity. Our last 2 examples are increasing at a decreasing rate. Okay, so I need to be increasing, so going up, but my slopes, that's the word rate again, my slopes have to be decreasing. So I think it's going to look like this, and hopefully you'll agree. If I put tangent lines on there for slope, are they getting smaller, closer to 0, or are they getting bigger? Well, again, if I had to assign maybe a +6 here, I would definitely say they're getting smaller, closer to 0. So my first derivative is positive. Again, that's describing slope. My second derivative is describing concavity, and this is concave down like a frown. Decreasing at a decreasing rate. All right, so based off my previous picture, I would say this would, well, that's a pretty bad one. Whoops. Oh boy, let me scratch that. Sorry, I can't erase. Decreasing at a decreasing rate. So again, if I put little tangent lines on there, that has a slope of 0. Now this is -1, -2, -4. These are actually getting smaller. They're getting more negative. So my slope is negative. Okay, remember that's your f prime describes slope. Your second derivative is also negative. And that's your concavity. All right. So I'll quiz you frequently on these, but you should be able to talk your way through it. Remember, the 4-letter word rate is just another word for slope. All right, in the next few examples, you're going to want to copy these tables in your notebook. It says let f be a differentiable function that is strictly monotonic with no inflection points. So you're probably going to see this word more frequently, monotonic, and all that's saying is that your function is doing one thing, mono meaning one. Either your function is strictly increasing or strictly decreasing. It's not doing both, it's doing one thing. Okay? Determine the sign of f prime and f double prime for the given table. State whether f is increasing at an increasing rate, increasing at a decreasing rate, decreasing at an increasing rate, or decreasing at a decreasing rate. So this is actually fairly simple. Basically, I need to determine if my function is increasing or decreasing first. And I think if you just look at the y values, that should give it away. If I went from 7 to 10 to 12 to 13, I would say that this function is strictly increasing. And I know strictly because of the word monotonic up there. Now, think about your sign chart. If I label this f prime and f, and I put a plus sign here, that told me f was increasing. That meant your first derivative is positive. So if I know my function is increasing, I automatically know f prime of x is greater than 0. Now I have to find something out about my second derivative. I have to see if I'm increasing at an increasing or decreasing rate. And that 4-letter word rate, every time I saw that, that's telling me to look at the slopes. And remember, the slope formula is just the change in y over the change in x. So what did I do? I'm just going to go through and find the change in y and the change in x and write the slope for each one. So the difference between 7 and 10 is 3. 10 and 12 is 2. 12 and 13 is 1. Change in the x's, that's a 1, and a 1. All right, so now I can calculate the slope of each one. I've got 3 over 1, 2 over 1, and 1 over 1. My slopes went from 3 to 2 to 1. So I know that my function is increasing, but my rate, or my slopes, I would say, are decreasing. So my function is increasing at a decreasing rate. Remember, rate means look at slopes. Let's try the next table. Okay, right off the bat, is your function increasing or decreasing? Okay, so I automatically should know that my function is increasing. And when I talk about increasing, decreasing, maxes, and min, those all talk about the first derivative. If my function's increasing, f prime is greater than 0. Now let's go take care of our rates. What are our slopes doing? So I'm going to find the change in y over the change in x. All right, so my y values are 3, 5, and my x values look like 2, 3, and 2. All right, so now let's go get our slope, our change in y over change in x. Okay, I would say I'm going from 3/2 to 5/3 to 5/2. All right, so if that bothers you, get a common denominator. I'm going to say I have a denominator of 6. Okay, so that's 9/6 to 10/6 to 15/6. What did my slopes do? Well, they just got from 9/6 to 10/6 to 15/6, they got bigger. So I would say that my function is increasing at an increasing rate. And that increasing rate, remember, means the slopes are increasing. All right, take a look at the next one. My y values got smaller, so my function is clearly decreasing. And if I put a minus sign here and a decreasing sign, that means f prime is negative. And now let's look at the slopes. Get that change in y over change in x. So I've got 2, 2, and 2. The difference between these two, that's going to get me a -5, a -4, and a -2. All right, so I've got -5/2, -4/2, and -2/2. Now look what your rates did in that order. If you went from -5/2 to -4/2 to -2/2, did you actually get bigger or smaller? I would say you definitely got bigger. So I am decreasing at an increasing rate. My slopes got bigger. Lastly, if you follow those y values, I think it's obvious that you're decreasing, so f prime is less than 0. And we'll get our change in y and change in x. That's a 3, a 2, and a 5. And if I go get my change in y, what does that get me? -1, -3, -9. So I've got -1/3 to -3/2 to -9/5. Okay, and if you can't tell, like I said, get yourself a common denominator, and you would see that these slopes are decreasing. So I would say I'm decreasing at a decreasing rate. All right, so the key idea is make sure you understand the word rate means you're looking at the slopes. All right, so let's apply this to some real world problems now, and this is actually an old AP question, something that you'll see a lot of pretty soon. Traffic flow is defined at the rate at which an automobile passes through an intersection measured in automobiles per minute. The traffic flow at a particular intersection is modeled by function f. All right, so I slow down and I really highlight things for myself, and I think you should do the same. I want to be clear that this represents traffic flow, and its units are automobiles per minute. All right, units are going to be a big deal, and make sure you know who you're talking about. Now here's the question. Is traffic flow, okay, that's the word I just wrote down, is this traffic flow I have increasing or decreasing at t equals 3? Now previously during the week here, we've talked a lot about the words increasing, decreasing, maxes, and min, and those words should be jumping off the page at take the derivative. Now you don't have to guess. It's saying take the derivative of traffic flow. So my goal is to find f prime of t. So I'm going to start by rewriting what f of t is. Of course, raise that to the 1/2 minus the cosine of pi t plus 20. And I know I need its derivative. And what gave it away again? The word increasing and decreasing. So on paper, I should say f prime of t equals, we'll take the derivative. That gets me 2 times t plus 1 to the -1/2 times the derivative of the inside. Derivative of cosine is negative sign, so that's a positive sign of pi times t. The derivative, its inside, is pi. 20 obviously is a constant. Now I have to have that on my paper. The next thing I have to show is substituting 3 into the derivative. Okay, so notice I first have the f prime of t, now I have f prime of 3. So I've got 2 times 3 plus 1 is 4 to the -1/2 plus the sine of 3 pi times pi. All right, so again, this is clearly non-calculator, which is no big deal. I know this chunk actually goes to the bottom, so I'm going to say that's 2 over. 4 to the 1/2 is really the square root of 4. Plus, I'm going to bring out the pi in front, the sine of 3 pi. So I get, whoopsie, that's really 2. 2 over 2 is 1 plus. Now the sine of 3 pi, perhaps you don't have memorized, but that's no big deal. Draw out your curve and talk yourself through it. This was 0. This is 1 pi. I'm sorry, that's pi over 2. This was 1 pi. 3 pi over 2, 2 pi. Where do you think 3 pi is going to take you? If that was 0, that was pi, that's 2 pi. Where the heck do you think 3 pi is going to take you? Well, of course it's going to take you to 0, which happens to be awesome because 0 times pi is 0. So I get a value of 1. Now, the question says, what is the traffic flow doing? Is it increasing or decreasing? Well, look at the answer you got. And again, we don't care what the number is per se, we care about the sign of the number. This is a positive number. F prime of 3 is greater than 0. I don't even need to say that it's 1, I need to say that it's positive. Therefore, f of 3 is increasing. Now notice, I didn't say f of t, I said specifically at 3. F of 3 is increasing. Part B. At t equals 3, is the traffic flow increasing at an increasing rate, increasing at a decreasing rate, decreasing at a decreasing rate or decreasing at an increasing rate. Basically, I already know it's not decreasing. I found that out in part A, so I'm going to scratch all those out. Either I'm increasing at an increasing rate or increasing at a decreasing rate. Whew. All right, we know our function's increasing. We can check that off the list from part A. Now the rate is telling me to look at its derivative. So I now need f double prime of t. So I'm just going to start by taking with whatever f prime of t was. So I'm going to go back and rewrite down what f prime of t was. And I think that was 2 times t plus 1 to the negative 1/2 plus pi sine of pi t. And I'm going to take its derivative and evaluate it at 3. So f double prime of t equals, that's going to be a negative t plus 1 to the negative, if I subtract 2 over 2, 3 over 2 times the inside, plus I've got pi times the cosine of pi t times pi. All right, notice I left my pi out front there. Now I took the derivative of the outside, keep the inside, derivative of the inside. So as I clean that up, let's see, I'm going to get f double prime of t equals, I'm going to rewrite this as negative 1 over the square root of t plus 1 cubed plus pi times pi gets me pi squared cosine of pi t. And now I'm going to carefully plug in the number 3. Negative 1 over the square root. 3 plus 1 is 4. 4 cubed is 64. Plus pi squared times the cosine of 3 pi. All right, so I get negative 1/8 plus pi squared, cosine of 3 pi, so picture that cosine graph. That's 0, that's 1 pi, that's 2 pi. Where do you think 3 pi is going to fall? So I'm going to say times a negative 1, so that's going to be a negative pi over 2. Now notice, I don't really care what this answer is. Again, I care about the sign. This is clearly a negative number. Therefore, f double prime of 3 is less than 0. So I can clearly state that my function is increasing at a decreasing rate because f prime of 3 was greater than 0 and f double prime of 3 is less than 0. All right, our next example, again, straight from the AP, the wording, I can't stress enough how important it is to slow down, identify who you have and what you want. This one is a little slightly different from the previous one. From 0 to 30, the rate of change of the number of mosquitoes on Malaria Island at time t is given by this equation, m of t, in mosquitoes per day. There's a ton of information I just read that we've kind of skipped over fast. I want you to write down the word rate of change of the number of mosquitoes. When I say the rate of change, I am telling you that is the derivative of the number of mosquitoes. Okay? Watch these units. They're in mosquitoes per day. That is a rate. Okay, that is a slope, a rate, a derivative. Part A says, is the number of mosquitoes increasing or decreasing? All right, so increasing and decreasing are the calc words that mean take the derivative. Now always ask yourself, who do they want the derivative of? Well, it says, is the number of mosquitoes increasing or decreasing? So I want the derivative of the number of mosquitoes. Does that pop out to you? It's got to. Remember, they just said the rate of change of the number of mosquitoes or the derivative of the number of mosquitoes is given here. I don't have to do any calculus. They're giving me the derivative of mosquitoes. So all I'm doing in part A is evaluating m of 6. Now let's just be clear on why. I know I have to take the derivative of the number of mosquitoes. Okay, and this equation represents the derivative of the number of mosquitoes. Now notice they didn't use that word derivative, they used rate of change instead. So I've got 36, that's my 6 squared, times the sine of pi over 6. So I basically have 36 times 1/2. I could write 18, which is obviously the answer, and that is mosquitoes per day. But the real question is the number of mosquitoes increasing or decreasing? And I am certainly going to say the number of mosquitoes is increasing And how do I know that? M of 6 is greater than 0, and that is my justification. Notice I didn't say M of t, I said M of 6, specifically at time t equals 6. Now let's throw part B in. Part B says at time t equals 6 is the number of mosquitoes increasing at an increasing rate, increasing at a decreasing rate, decreasing at an increasing rate, or decreasing at a decreasing rate. Well, I already know it's increasing, so I'm going to immediately get rid of those options. I'm either increasing at an increasing rate or increasing at a decreasing rate. And that rate is the key that gives it away. That is telling me to take the derivative of my function. So I am now looking for m prime of t. So I'm going to restart my function with m of t. And this one's a little sneaky. There's a little bear trap in there, so be careful. My m of t function was t squared sine of pi over t. Now, you might be thinking that doesn't really look any different. I'm not sure what she's talking about by bear trap, but rewrite this function careful. I'm going to slow down and say this is m of t equals t squared times the sine of pi t to the negative 1. All right, slow down and rewrite. So now when I take my derivative, notice I said times, I've got a nice product rule there. So I'm going first. The derivative of the second is the cosine, keep the inside, times the derivative of the inside, negative pi t to the negative 2, plus the second sine of pi t to the negative 1 times 2t. All right, now before I dare plug that 6 in, I am going to clean this up because this just looks horrendous. I've got t squared. This is the cosine. I'm going to put that back as pi over t times negative pi over t squared plus, I'm going to pull that 2t out front, 2t sine of pi over t. All right, now I'll just evaluate m prime of 6. So that's 36. I get the cosine of pi over 6, which is, of course, is the cosine of 30, which is radical 3 over 2, times negative pi over 36, plus 6 times 2 is 12. Sine of pi over 6 is 1/2. All right, so 36 and 36 cancel, so I basically get negative pi, radical 3 over 2, plus 6. Now the question is, who's bigger? Is the 6 greater, or is the negative pi over 2 times radical 3 bigger? Well, don't get stuck on this and don't get too scared. Remember, pi is approximately 3.14. All right, so keep that in mind. That's 3.14. The square root of 4 is 2. The square root of 1 is 1. So I know that falls between 1 and 2. So I'm going to say like it's 1.9 or something. And I'm dividing that by 2. Clearly, 3 times 1 divided by 2 is going to be less than 6. So I know this number is positive. So I can say my function is increasing at an increasing rate, okay, because m of 6 is greater than 0 and m prime of 6 is greater than 0. All right, our last example, again, straight from our AP. The rate in calories per minute at which Mackenzie burns calories while running a race is modeled by this function. At what time is C increasing at its greatest rate? Show the work that leads to your answer. Well, right off the bat, I see my favorite calc word, increasing, which is telling me to take the derivative. And who do they want to know is increasing? C. So let's start by finding C prime of t. All right, real nice and easy. I get negative t squared plus 11t. I can factor out that t. I can factor out a negative t, I guess. And I get t minus 11. So I've got t equals 0 and t equals 11. All right, now, notice that there are endpoints there. All right, so I've got 0 to 20. I've got an 11. I've got my C prime, C. I'm going to test a 1 and a 12, plug them into the derivative. So I'm going to get, when I plug a 1 in, I get a negative times a negative is a positive. When I plug a 12 in, I get a negative times a positive is a negative, which tells me I'm increasing and then decreasing. So basically what I've discovered is that C is increasing on the interval 0 to 11. Now the question says, at what time is c increasing at its greatest rate? So I know that it has to fall sometime between 0 and 11 because otherwise the function's decreasing. Now to figure out what time that happens, I need to look at c double prime. So let's quickly take its derivative, negative 2t plus 11. So I've got equals 0. T equals 11 halves. So we'll make a sign chart. We've got 11 halves. Remember, our interval only went from 0 to 20. C double prime. 11 halves, well, 2 goes into 11, 5 and a little more. So you can pick anybody before 5 and anybody after 5. I'm going to pick a 1 here. That gets me a positive. I'm going to pick a 10 here. That gets me a negative. So I know I am increasing at my greatest rate when t equals 11 halves. Well, that does it for us tonight. We'll look forward to some great practice tomorrow. Have a great night.